In this problem, we are presented with a manometer that's being used to measure the pressure drop across some sort of flow device. This is a U-tube manometer. Um, U, the letter U-tube, not YOU, like the video platform. Um, and we're asked to find an expression for the pressure difference that's being measured by this flow device. Um, and we're told that we have some location in the channel A relative to some location, looking at that pressure relative to the pressure at some location in the channel B. Um, the fluid that's flowing has density given by rho1, and the fluid that fills the U-tube manometer has a pressure, sorry, a density rather, that's given by rho2. And we want to find a general expression for this. And then I've added on to this another question, which is what is HF? Well, what is the head loss due to friction because of that flow device? And so once we have the delta P, we'll look at an energy balance and see what it tells us about the head loss due to friction. All right, so to begin this kind of problem, we're basically just going to be applying our expression for hydrostatic for pressure in a hydrostatic fluid of delta P is equal to minus gamma delta Z. Noting here that although there's flow going on within this top channel, right, so we have flow going through that flow device, um, within the manometer tube underneath, we have a fluid static condition. So we don't have any flow going on within the manometer itself, assuming that we've reached steady state and everything has settled out. So in that case, we can use our expression um, delta P is equal to minus gamma delta Z sequentially to solve this kind of problem. So to help us get started on this, I think it's helpful to label all the different locations within this system. Um, and we'll label them starting um, from here, I think. I'm going to call this point 1, call this 2, call this 3, call this 4, and then finally this location is 5. And then we'll note that PA is equal to P1, but I think by writing it out like this, it'll help us keep track of it a little bit better. And we're just going to march from position 1 back to position 5 applying this equation, delta P is equal to minus gamma delta Z. So let's start from 1 to 2. All right, so we're within a single connected fluid there from 1 to 2. And so we can say that P1 minus P2 is equal to minus rho 1 G times Z1 minus Z2. And now I'm going to define in this problem this location to be Z is equal to 0. And so now this is going to be equal to minus rho 1 G times Z1 is going to be L plus H minus Z2 is just H. So I have P1 minus P2 is equal to minus, those H's are going to cancel out, so minus rho 1 G L. Or if I rewrite this, I get P2 is equal to P1 plus rho 1 G L. We can just do a sanity check here. L is positive, rho is positive, and so this expression implies that P2 is greater than P1, and that makes sense because point 2 is lower within this fluid than P1 is, and we know that pressure goes up as we move down within a fluid in a hydrostatic condition. Okay, so that makes sense. Now we're going to go from 2 to 3. Here, let's just use that intuition that pressure goes up as we move down within a fluid, and we can take a little shortcut and say P3 is equal to P2 plus, right, because pressure is going down from 2 to 3. And this is going to be rho 2 times G times H, right, which is the height difference between 2 and 3. All right, so we know P2 in terms of P1, P3 in terms of P2. And we know that P4 is equal to P3 because point 4 and point 3 are at the same height within this connected fluid, that fluid 2, the fluid with density rho 2. And then now we're going to move up to position 5. And let's do our delta P is minus gamma delta Z. So we'll say P, say 5 minus P4 is equal to, let's turn that up, is equal to minus, this is again going to be rho 1 G times Z5 minus Z4 is equal to minus rho 1 G times, so again, Z5 here is L plus H, and Z4 is 0. Right? So therefore, we're going to have P5 equal to P4 minus rho 1 GL minus rho 1 GH. Okay, and now let's put it together. This P5 is equal to PA, and we know that P1 is equal to PB. So let's plug this all in and work our way backwards. So we have PA is equal to, I'm going to write this out. I'm going to expand this out as we go. So PA, so let's do a little bit of rearranging here, is equal to minus rho 1 GL minus rho 1 GH plus P4. P4 is just P3, and P3 is given right here. So it's going to be plus rho 2 GH plus P2, and this is P2, so plus rho 1 GL plus P1, which is that at that point B, so it's plus PB. And we can see here that we have rho 1, we have minus rho 1 GL plus rho 1 GL, so these things drop out. I'm going to bring my PB over to the other side, so I'm trying to find the pressure difference, PA minus PB. So we have PA minus PB is equal to, I have this common term of GH, so I'm going to write this out as GH times rho 2 minus rho 1. Right? So we said that for this kind of a U-tube manometer setup, the difference in pressure between A and B is gravitational acceleration times the height that we measure in this column times the difference in densities. And you notice here that this this length L between where the flow channel is and where the upper height of the fluid column reaches drops out of this expression. But rho 1 does not. So in this case, rho 1, or the pressure difference here is related to the difference in densities between rho 2 and rho 1. Now, if we were to have something like water as our fluid 2 and air as our fluid 1, we have 1,000-fold difference in density, then this delta here is negligible. We can get away with just using rho 2. But in cases where the fluid in the manometer and fluid in the flow device have similar densities, then this can definitely be really important. So the second piece that I'm asking here is, what is HF, right? So to find HF, we're going to have to use the energy balance expression. And this way we can actually then relate the head loss due to friction through this flow device, whatever it is, to the measured pressure that we got within this manometer. So let's look at that. So if we have, so we're going to say P over, so let's leave it as gamma for a second, plus alpha over 2G squared plus Z in is equal to P over gamma plus alpha over 2G B squared plus Z out plus HF minus HP plus HT, where HP and HT are so the pump in a turbine, or the energy associated with a pump or turbine. In this case, we're going to assume that those things are zero, because we're just really asked to find HF. The Z, right, between inlet and outlet is the same if we're now considering just whatever is going on through this flow device. ZA is equal to ZB, and so Z's are the same. And haven't said anything about the area between section A and section B, but from this drawing, it looks like the areas are the same. So if A1 is equal to, call that if A is equal to AB, then by mass conservation, by V A is equal to V B A B, then V A is equal to V B, and that means that these velocity terms are going to cancel out as well. And so we're just going to be left with an expression relating the pressure in to the pressure out plus that head loss due to friction. But before we do that, we have to resolve what this gamma thing is, right? And this is a little bit confusing, right? Because there's a couple of densities that we have within this problem. But when we're considering this expression here, this is all written in terms of what's happening within the flow through this device, which is all within fluid 1. So this is all gamma for fluid 1. So we can actually rewrite this as gamma 1. And so simplifying this and plugging in our expressions for, or our letters for A is the inlet and B is the outlet, we're going to have that P A over rho 1 G is equal to P B over rho 1 G plus H F. And so we can rewrite this now as HF is equal to 1 over rho 1 G times PA minus PB. And we have an expression for PA minus PB just given right up here. So if we just plug that in, so we're going to get this equal to 1 over rho 1 G times G H rho 2 minus rho 1. G drops out. And so our HF, therefore, just to simplify a little bit, is going to be H, the height that we measured within that manometer U-tube, times rho 2 minus rho 1 over rho 1. So there we go. So we've now related, or used our energy balance equation to relate the reading that we get from our manometer tube. Actually, that reading is really this value H here, right? So relate the reading that we get from our manometer tube to the head loss due to friction. We can just do a quick dimensional analysis of this to make sure that everything is working out as we would expect. We know that head loss due to friction, this has dimensions of length, Um, the height there is an actual physical height, so that has dimensions due to length, dimensions of length. And when we take delta rho, that still has the same dimensions as rho, and dividing that by rho means that we're just multiplying by something that's dimensionless. And so we have L is L, and therefore this expression at least is dimensionally consistent. So there we go. That was an example of fluid statics, but also how we can use that to learn something about energy balance as well.